When you hear the word muon, it sounds small, almost forgettable. But right now, as you sit here, muons are quietly passing through you, born high above the clouds, traveling close to the speed of light, living only for a fleeting moment before they vanish. They are heavier cousins of the electron, identical in every way that seems to matter, and yet somehow they exist at all. Why would the universe create a particle so short-lived, so unstable, and then scatter it endlessly through our atmosphere? Why does it behave exactly like an electron but refuse to stay? And what does its brief existence reveal about time, mass, and the hidden structure of reality? Tonight, we slow everything down. We follow the muon from the edge of space to the surface of the Earth, from quiet equations to surprising experiments, not to rush toward answers, but to rest with the question itself. What is a muon really? When physicists say the word muon, they are not naming an object you could ever point to or hold. They are naming a pattern, a recurring event in nature that appears, briefly, behaves precisely, and then disappears without leaving a trace behind. At first glance, the muon seems almost redundant. It looks exactly like an electron. It carries the same negative electric charge. It has the same intrinsic spin, one half the same quantum twist that allows it to interact with magnetic fields and obey the same exclusion rules as electrons in atoms. If you wrote down the equations that describe how an electron moves through space, responds to forces and couples to light, you could reuse nearly all of them for a muon. And yet the universe insists that the muon is something distinct. The first question then is not what does a muon do, but what kind of thing is it? Is the muon truly fundamental, or is it a temporary state of something deeper? Every experiment performed so far answers in the same quiet way. When probed at smaller and smaller distances down to scales far beyond what atoms or nuclei occupy, the muon shows no internal structure. It does not break apart into components. It does not reveal layers. Within the limits of measurement, it behaves as a point-like particle, just as electrons do. In the language of modern physics that places the muon among the elementary particles, entities not known to be composed of anything smaller. More specifically, it belongs to a family called leptons. This distinction matters because the particle world is divided sharply by how particles interact. Hadrons, such as protons and neutrons, feel the strong nuclear force and are built from quarks bound together. Leptons do not. A muon passes through space without ever experiencing the strong force. It interacts only through electromagnetism, the weak interaction, and gravity. This immediately separates the muon from the particles that make up everyday matter. Protons and neutrons form atomic nuclei. Electrons form atomic shells. Muons do neither. They do not build stable structures. They do not accumulate. They appear, move, and vanish. Their existence is transient by design. And yet, despite their fleeting nature, muons are not rare. High above the surface of Earth, cosmic rays, particles accelerated by distant astrophysical events, collide with atoms in the upper atmosphere. These collisions create short-lived particles called pions, which then decay almost instantly into muons. Those muons rain downward constantly. Every second, several pass through your body without notice, without sensation, without harm. This brings us to the most striking difference between muons and electrons' mass. A muon is about 200 times heavier than an electron. That single number changes everything. It determines how the muon moves, how long it survives, how deeply it penetrates matter, and how sensitive it is to subtle quantum effects. Because the muon is so much heavier, it is unstable. It does not last. On average, a muon survives only a few millionths of a second before decaying into other particles through the weak interaction. This decay is not caused by collisions or external forces. It happens spontaneously. The muon simply transforms. The electron, by contrast, appears perfectly stable. No experiment has ever observed an electron decaying. If it does decay, its lifetime is far longer than the age of the universe. The muon sits in a strange middle ground, too heavy to be stable, too light to form complex bound states, existing just long enough to be measured, but not long enough to linger. Why does this matter? Because it tells us that mass is not just a number attached to a particle. It is a structural property that determines whether something can exist indefinitely or only briefly. The muon's mass comes from the same source as the electron's mass, its interaction with the Higgs field. But the reason its value is so much larger remains unexplained. This leads to one of the most persistent puzzles in particle physics. If muons and electrons are identical in every way except mass, why does nature include both? Why not just electrons? Why introduce a heavier copy that decays almost immediately? The Standard Model describes how this works with perfect precision, but it does not explain why it is so. Physicists group leptons into 3 generations: electron, muon, and tau. Each generation is heavier than the last. Each behaves the same way, differing only in mass and stability. The muon is the middle generation, heavier than the electron, lighter than the tau. No known principle demands that this structure exist. It is simply observed, and that observation has never stopped being unsettling. Does the muon have a size? In everyday language, size implies spatial extent. But when physicists talk about the size of a fundamental particle, they mean something different. They ask whether the particle shows any internal spread when scattered at high energies. So far, the answer for the muon is no. All experiments are consistent with the muon behaving as a mathematical point. This does not mean the muon is infinitely small in a physical sense. Rather, it means that within the resolution of our measurements, no boundary or substructure appears. The muon interacts as though all its properties, charge, mass, spin, are concentrated at a single location in space. Those properties themselves are precisely defined. The muon carries a negative electric charge equal in magnitude to that of the electron. This charge determines how it curves in magnetic fields and how it ionizes matter as it passes through. The muon also has spin 1/2 an intrinsic angular momentum that is not literal rotation but a quantum property with real physical consequences. Because it has both charge and spin, the muon behaves like a tiny magnet. This magnetic character is described by a quantity known as the magnetic moment. For a simple point particle, this value can be predicted extremely accurately. And for the muon, that prediction becomes a powerful test of the quantum vacuum itself. Why? Because the muon is heavy. Its large mass allows it to interact more strongly with fleeting quantum fluctuations, virtual particles that appear and disappear in empty space. These interactions slightly alter its magnetic moment. Measuring that alteration allows physicists to detect the influence of particles that cannot be seen directly. In this way, the muon becomes more than a particle. It becomes a probe, a sensor, a messenger carrying information about the deepest layers of physical law. Its brief life is not a weakness, but a feature. The fact that it decays forces experiments to be precise. The fact that it is heavy amplifies subtle effects. And still the most basic question lingers. Is the muon truly fundamental, or is it hinting at something incomplete in our understanding? At present, every measurement says it is fundamental, but history has shown that particles once thought indivisible can later reveal hidden structure. For now, the muon remains exactly what experiments say. It is a point-like lepton, heavier than the electron, unstable but abundant, identical in behavior, yet different in fate. It does not build matter, it does not persist, but it passes through the universe continuously, quietly carrying clues about mass, time, and the unseen activity of the quantum world. And with that quiet persistence, the muon earns its place, not as a curiosity, not as a duplicate, but as one of the clearest windows we have into what fundamental truly means. If muons lived only as long as the equations say they should, the Earth would be a quiet place for particle physicists. A muon at rest survives on average just a few millionths of a second. That is far too short for a particle created high above the planet to reach the ground. And yet muons arrive at the surface, constantly passing through buildings, mountains, and bodies, as if the planet were almost transparent. This apparent contradiction is the first clue that muons are not rare accidents, but a natural consequence of how the universe delivers energy to Earth. The story begins far beyond the atmosphere, in regions of space where charged particles are accelerated to extraordinary energies. These particles, mostly protons, sometimes heavier nuclei, are known collectively as cosmic rays. They originate from violent astrophysical processes, shock waves from supernova explosions, turbulent magnetic fields around neutron stars, and energetic environments near black holes. Once launched, they travel for thousands or even millions of years, crossing interstellar space before encountering a planet. When a high-energy cosmic ray reaches Earth, it does not stop gently. It strikes the upper atmosphere at enormous speed, colliding with molecules of nitrogen and oxygen. This collision is not a simple impact. It is a particle physics event, releasing energy that reorganizes itself into new particles almost instantly. The first products of this collision are unstable hadrons, primarily pions and kaons. These particles exist only briefly, but they carry the energy of the original cosmic ray downward. They are born moving close to the speed of light, and because of that speed, their short lifetimes stretch just long enough for them to travel before decaying. Pions, in particular, play a central role. A charged pion decays into a muon and a neutrino. This decay is governed by the weak interaction and happens predictably almost every time. The neutrino escapes, barely interacting with anything. The muon continues downward, inheriting most of the pion's momentum. This process repeats again and again across the sky. At any moment, countless cosmic rays are colliding with the atmosphere, generating cascades of secondary particles known as air showers. Muons are one of the most numerous and long-lived products of these showers. They form a continuous, invisible flux reaching the ground. The reason muons survive the journey lies in their speed. Most atmospheric muons travel at velocities extremely close to the speed of light. According to special relativity, time does not pass at the same rate for objects moving that fast. From the perspective of an observer on Earth, the muon's internal clock runs slowly. What should be a lifetime of a few microseconds becomes long enough tens of microseconds to allow the muon to cross many kilometers of air. From the muon's own perspective, something else happens. The distance between its point of creation and the Earth's surface is shortened. The atmosphere becomes thinner in the direction of motion. Both descriptions are valid. Both lead to the same outcome. Muons arrive at the ground in large numbers. Once they reach the surface, muons continue moving with remarkable persistence. Because they are heavy compared to electrons, they lose energy slowly as they pass through matter. Their primary interaction is ionization. They nudge electrons out of atoms along their path, depositing small amounts of energy as they go. But these interactions are gentle. A muon does not stop easily. This is why muons can pass through walls, vehicles, and even thick layers of rock. While most particles from cosmic ray showers are absorbed high in the atmosphere or blocked by solid material, muons penetrate deeply. Some reach underground laboratories hundreds of meters below the surface. Others pass entirely through mountains before decaying. The steady arrival of these particles is often called muon rain, though there is nothing wet or visible about it. The term simply reflects constancy. At sea level, roughly 1 muon passes through an area the size of a human hand every second. Over the entire surface of your body, that adds up to several muons per second, day and night. Their energies vary. Many atmospheric muons carry energies of a few billion electron volts, far greater than what is needed to penetrate solid matter. Some carry much more, depending on the energy of the original cosmic ray that produced them. Despite this, they pose little biological risk. The energy they deposit is small, spread thinly along their paths, and comparable to natural background radiation. What matters scientifically is not their hazard, but their reliability. Muons arrive predictably. Their rate depends on altitude, latitude, and atmospheric conditions, but it never drops to zero. This makes them ideal natural probes. Long before particle accelerators existed, muons provided evidence that new particles were constantly arriving from above. In the broader picture of cosmic rays, muons serve as messengers. They are not primary particles from space, but they preserve information about those primaries. The number, energy, and angular distribution of muons at the surface reveal details about the cosmic rays that produce them. By studying muons, physicists infer the composition and energy spectrum of cosmic radiation far beyond Earth. Muon measurements have also played a historical role in confirming fundamental physics. Early observations of muon flux at different altitudes helped verify relativistic time dilation. Without muons, this effect would remain an abstract prediction. With muons, it became measurable using detectors carried up mountains or aboard aircraft. Even today, muons remain indispensable. They allow scientists to study cosmic rays without leaving the planet. They enable underground experiments to distinguish rare signals from background noise. They reveal how high-energy particles interact with the atmosphere. Seen this way, muons are not anomalies. They are the natural byproduct of a universe filled with energetic processes. Earth happens to sit in their path. The atmosphere acts as a factory, converting distant cosmic violence into a steady, measurable stream of particles at the surface. The next time you consider the sky above you, it may seem calm and empty. But just above the clouds, collisions are constantly unfolding. Invisible chains of events link distant stars to the ground beneath your feet. Muons are one of the few traces of that connection that reach us directly, carrying with them the quiet evidence that space is never truly still. They arrive, they pass through, and they disappear. And in doing so, they remind us that even here, at rest on the surface of a planet, we remain immersed in the ongoing activity of the universe. If muons were easy to work with, they would have become ordinary tools long ago. But they are not. A muon lives briefly, arrives unexpectedly, and refuses to wait. That single fact shapes every experiment built around it. In nature, muons fall from the sky. In the laboratory, they must be made deliberately in carefully controlled bursts of energy. The challenge begins with the simple truth that muons cannot be stored in containers or bottled for later use. They must be created, guided, measured, and understood almost immediately after they appear. The process starts not with muons themselves, but with protons. In large accelerator facilities, protons are stripped from hydrogen atoms and accelerated to enormous energies using electric fields and radio frequency cavities. These protons are not accelerated for their own sake. They are accelerated because they are efficient carriers of energy, and because when they collide with matter, they produce the unstable particles that eventually decay into muons. Once accelerated, the proton beam is directed into a dense target, often made of graphite or metal. The collision is violent at the subatomic scale. The proton's energy does not disappear. It reorganizes itself into new particles. Among the most important of these are pions and kaons, short-lived hadrons that form abundantly when high-energy protons strike nuclei. These newly created pions and kaons emerge moving at high speed. Almost immediately, they begin to decay. Charged pions decay primarily into muons and neutrinos. Charged kaons follow similar decay paths, though, with different probabilities and energies. The neutrinos escape unnoticed. The muons remain. At this point, the laboratory is flooded with many kinds of particles, all moving in slightly different directions and carrying different energies. To use muons for precise experiments, physicists must isolate them from this chaos. This is where magnetic fields become essential. Because muons carry electric charge, their paths curve in magnetic fields. By shaping the magnetic field carefully, unwanted particles can be bent away, while muons, with the desired momentum, are guided forward. This selection process creates what is known as a muon beam, a stream of muons traveling together with controlled direction and energy. Creating a muon beam is an exercise in timing and geometry. The parent pions must be allowed to decay, but not too late. If they decay too early, the resulting muons may scatter. If they decay too late, they may be lost. Beamlines are designed with decay channels, long evacuated regions, that give pions space to transform into muons before reaching the next stage of selection. Vacuum plays a crucial role here. Air would scatter particles and absorb energy. Inside beamlines, pressure is reduced to near empty space, allowing muons to travel unimpeded. This vacuum environment ensures that their trajectories remain predictable and that their energies remain well defined. Once a muon beam is formed, it must be shaped. Magnetic lenses focus the beam, narrowing its spread. Bending magnets steer it toward experimental areas. Every adjustment is calculated with care because muons do not wait. Their lifetime continues to tick away as they move. This short lifetime is what makes muons both powerful and difficult. On the one hand, their decay is governed by the weak interaction, which is precisely described by theory. Measuring muon decay allows physicists to test fundamental principles with high accuracy. On the other hand, the decay happens quickly, forcing experiments to operate on timescales of microseconds or less. Timing systems become essential. Detectors must register the arrival of a muon, track its path, and record its decay products almost instantaneously. This requires fast electronics, synchronized clocks, and carefully calibrated sensors. Any delay risks losing the event entirely. Muon detectors vary depending on the experiment. Scintillators produce flashes of light when a muon passes through. Drift chambers record the ionization trails left behind. Silicon detectors provide precise spatial resolution. In many experiments, multiple detector types are layered together to cross-check measurements and reduce uncertainty. Magnetic fields often surround the detector region as well. These fields cause charge decay products to curve, allowing physicists to infer their momenta. From these curves, the properties of the original muon can be reconstructed. Even though the muon itself vanishes, its presence is inferred through the patterns it leaves behind. Some experiments require muons to be slowed down. This may seem counterintuitive, since muons are born fast and decay quickly. But slowing them allows them to be captured into bound states, such as muonic atoms, where a muon replaces an electron. Achieving this requires carefully designed absorbers that reduce muon energy without stopping them entirely. Other experiments require the opposite muons kept at high energy circulating in storage rings. In these setups, powerful magnetic fields hold muons in circular paths. As they circulate, their properties can be measured repeatedly until they decay. This approach is used in precision measurements of the muon's magnetic behavior, where even tiny deviations carry enormous significance. Every aspect of muon experimentation reflects a balance between control and urgency. The particle is cooperative in one sense. It behaves exactly as theory predicts in most situations. But it is unforgiving of delay. Instruments must be ready before the muon arrives, not after. This is why muons have shaped experimental culture in physics. They demand coordination between accelerator physics, detector engineering, electronics, and data analysis. A successful muon experiment is never the result of a single component working well. It is the result of everything working together at the right moment. Despite these challenges, muons remain invaluable. Their large mass makes them sensitive to effects that electrons barely notice. Their decay reveals the structure of the weak interaction. Their interactions with magnetic fields probe the quantum vacuum. No other particle offers the same combination of accessibility and depth. In the laboratory, muons are not just particles to be observed. They are tools that interrogate theory. Each one carries information from the instant of its creation to the instant of its disappearance. And when the experiment ends, the muons do not remain. They leave no residue. They do not accumulate. They simply transform, handing their energy to other particles and returning their borrowed existence to the fabric of physical law. What remains are numbers, traces, and timing signals, records of events that unfolded too quickly to be seen yet slowly enough to be measured. And through those records, muons continue to teach physicists how to work at the boundary between precision and impermanence, where even the shortest-lived particles can speak clearly if one listens fast enough. A muon never promises to stay. From the moment it comes into existence, it is already on its way out. Is less than #0. 5# is greater than. There is no warning, no gradual fading, no sign that the end is approaching. One moment the muon exists, carrying charge and mass through space. The next moment, it does not. Something else takes its place. This fleeting nature is not a flaw of the muon. It is its defining feature. On average, a muon survives for about 2 millionths of a second. That number is precise, but the meaning behind it is subtle. In quantum mechanics, average does not mean that every muon lives for exactly that duration. It means something quieter and stranger. If you were able to line up a vast number of identical muons and start a clock at the instant they were created, you would not see them decay one by one in orderly fashion. Some would vanish almost immediately. Others would persist longer than expected. A few would linger far beyond the average. What emerges from this randomness is not a schedule, but a pattern. That pattern is exponential. At every instant, each muon carries the same probability of decaying, regardless of how long it has already survived. A muon does not age. It does not become fragile with time. Its chance of disappearing in the next moment is always the same. This is what lifetime truly means. It is not a countdown. It is a statistical signature. It tells us how a population fades, not how an individual behaves. And this idea, so natural in quantum physics, runs directly against everyday intuition. When a muon does decay, it does not break apart the way a macroscopic object would. It transforms. The muon ceases to exist as a muon, and in its place appear other particles, an electron, a muon neutrino, and an electron antineutrino. Nothing explodes. Nothing fragments. The transition is clean, precise, and governed by a single interaction, the weak force. The weak interaction is responsible for processes that change particle identities. It allows one type of lepton to become another. It governs radioactive decay. It operates quietly without binding particles together or generating long-range forces. This is why the muon decays through the weak force, rather than electromagnetism or the strong interaction. The electromagnetic force conserves particle identity. It can move energy around, bend trajectories, and create photons, but it cannot turn a muon into an electron. The strong force never acts on muons at all. Only the weak interaction permits this kind of transformation. At first glance, one might wonder why the muon does not simply relax into an electron by emitting light, the way electrons in atoms drop to lower energy states and release photons. But this comparison hides a crucial distinction. An electron in an atom occupies a bound energy level. It exists in a structured environment shaped by electromagnetic attraction to the nucleus. When it emits a photon, it is not changing its identity. It is changing its state within a system. A muon is not bound in that way. It is a free particle. There is no lower energy muon state waiting beneath it. There is no orbital to fall into. To become an electron, the muon must stop being a muon entirely, and that requires the weak interaction. When the decay occurs, energy must be conserved. The muon's rest mass represents a reservoir of energy, and that energy is redistributed among the decay products. Some of it appears as the mass of the electron. The rest becomes kinetic energy shared among the electron and the two neutrinos. But the sharing is not fixed. Each decay distributes energy differently. Sometimes the electron carries most of the energy, sometimes very little. The neutrinos, elusive and nearly massless, take the remainder. This variability is another hallmark of quantum decay. There is no preferred outcome for an individual event. Only the overall distribution is predictable. By measuring many decays, physicists build a spectrum, a smooth curve that reflects the underlying rules of the weak interaction. Detecting this process requires speed and patience at the same time. The muon itself is never observed decaying directly. Instead, detectors capture the electron that emerges. By measuring its energy and direction, and by correlating this with the time of the muon's arrival, the decay can be reconstructed. Timing becomes essential. The interval between muon creation and decay is measured again and again, building a decay curve that reveals the muon's lifetime with remarkable precision. Over decades, this lifetime has been confirmed to extraordinary accuracy, becoming one of the most reliable constants in particle physics. Yet for all this precision, the process remains fundamentally random. No hidden variable determines when a specific muon will decay. There is no internal clock counting down. The muon does not know how long it has existed. This randomness is not ignorance. It is intrinsic. It is woven into the structure of quantum theory itself. And in that sense, the muon becomes something more than a particle. It becomes a natural clock, one that ticks not by counting seconds, but by obeying probability. Physicists often speak of the muon lifetime as a benchmark. It is used to calibrate detectors, to test time dilation, and to validate theoretical frameworks. But beneath these applications lies a deeper lesson. The muon shows us that decay is not decay in the everyday sense. Nothing is wearing out. Nothing is failing. The muon is simply participating in a lawful process that allows change. Energy is conserved. Charge is conserved. Lepton number is accounted for through the neutrinos. Every rule is obeyed, and yet something genuinely new appears. An electron emerges where a muon once was. This quiet transformation is one of the clearest examples of how the universe balances permanence and impermanence. The muon itself does not last, but the pattern of its behavior does. Every muon follows the same statistical law, even though each one meets its end at a different moment. In this way, muon decay bridges two worlds. It is deeply unpredictable at the level of individual events, yet exquisitely predictable in aggregate. It is fleeting yet measurable, random yet structured. And perhaps that is why the muon continues to hold attention. In its brief existence, it compresses some of the most profound ideas in modern physics: the role of probability, the nature of time, and the meaning of change at the smallest scales. A muon does not linger long enough to be familiar, but long enough to teach. Of all the questions the muon asks of physics, none is more uncomfortable than this one. Why is it heavy? Not heavier in a vague sense, but heavier by a very specific amount, roughly 200 times heavier than the electron. Not 10 times, not 1,000, 200. Enough to change everything about its behavior, but not enough to make it a completely different kind of particle. This is the question physicists quietly call the muon's weakness, because it exposes a place where the equations still answer how, but remain silent about why. On paper, the muon looks almost like a copy of the electron. Same electric charge, same spin, same response to electromagnetic fields, same way of interacting with the weak force. If you were allowed to erase the mass term from the equations, you would struggle to tell them apart. And yet the universe insists on carrying both. If electrons exist, why add a second lepton that behaves the same way but weighs far more and vanishes almost immediately? Why duplicate the pattern? The Standard Model offers a precise mechanism for how the muon acquires its mass. Like the electron, the muon interacts with the Higgs field. This interaction resists the particle's motion through space, and that resistance appears as mass. In this sense, the muon is heavier because it couples more strongly to the Higgs field than the electron does. But this explanation stops exactly where curiosity begins, because the model does not tell us why that coupling strength has the value it does. It simply inserts the number, measure it, confirm it, use it. The muon's mass is not predicted, it is accepted. This places the muon in a peculiar position. Its mass is not arbitrary in the sense of being random noise. It is stable, consistent, and universal. Every muon ever observed has exactly the same mass. But that mass is not derived from any deeper principle we currently know. The situation becomes even more puzzling when the muon is placed into its family. Electrons are not alone. Muons are not alone. There is a third lepton as well, the tau. The tau behaves just like the electron and the muon, but it is far heavier still and far shorter lived. 3 generations, 3 copies of the same structure. Only the mass changes. Why 3? Why not 1? Why not 2? Why not an infinite ladder of increasingly heavy leptons? The Standard Model answers none of these questions. It only describes the pattern once it is observed. This repetition is not limited to leptons. Quarks come in generations too, each generation heavier than the last, each generation mirroring the same internal structure. The muon is part of a broader symmetry that spans the entire particle zoo. And that symmetry is unsettling, because symmetries in physics usually exist for a reason. They simplify equations, they preserve quantities, they arise from deeper constraints. But generational symmetry does none of these things cleanly. It adds complexity, it adds parameters, it adds masses that must be measured rather than derived. Some physicists suspect that the generations are shadows of something deeper. Perhaps they reflect a structure hidden at energies far beyond our current reach. Perhaps they emerge from a broken symmetry that once unified all leptons into a single object. Perhaps they encode information about extra dimensions or composite substructure. Others suspect something even simpler and more unsettling, that the generations may simply be facts about our universe, not consequences of deeper logic. That the muon is heavy because the universe happens to allow it, not because it must be. This tension sits at the heart of modern particle physics. Are the masses of fundamental particles calculable, or are they environmental? Are they dictated by principle or selected by circumstance? The muon refuses to answer. From a practical perspective, the muon's mass has enormous consequences. Its heaviness makes it unstable. It opens decay channels that electrons cannot access. It allows the weak interaction to transform it. Without its mass, the muon would be stable. With it, the muon becomes fleeting. The mass also amplifies quantum effects. Virtual particles that barely influence electrons leave measurable traces in muons. This is why the muon's magnetic behavior is such a sensitive probe of physics beyond the standard model. In this way, the muon's mass is both a mystery and a gift. It complicates the theory, but it sharpens the experiments. Still, this does not answer the deeper question. Why does the universe include a particle whose sole apparent purpose is to be heavier, shorter-lived, and more sensitive to quantum fluctuations? One tempting idea is that the muon plays a role in the early universe. Perhaps heavier leptons were important when temperatures were high and energies extreme. Perhaps their presence influenced how matter and radiation evolved. But current cosmology offers no compelling necessity for muons. The universe would still form atoms, stars, and galaxies without them. The muon does not stabilize matter. It does not shape chemistry. It does not determine large-scale structure. From a cosmic perspective, the muon looks almost redundant, and yet redundancy itself may be the clue. Nature often repeats patterns when underlying symmetries exist. The fact that the muon mirrors the electron so closely suggests that both may arise from a shared framework, one that expresses itself multiple times with different parameters. The repetition may not be wasteful, it may be diagnostic. In this view, the muon is not an accident. It is a probe built into the fabric of the universe, a way for physical law to test itself at different mass scales, while preserving the same interaction structure. Whether this interpretation is correct remains unknown. What is clear is that the muon exposes a limit of explanation. We can calculate its behavior to extraordinary precision. We can predict how it decays, how it moves, how it responds to fields. But we cannot yet say why its mass is what it is. This is rare in modern physics. Most quantities either vanish due to symmetry or are fixed by principle. The muon's mass does neither. It stands alone, measured but unexplained. And that may be why the muon continues to matter. It is not just a heavier electron. It is a reminder that our most successful theories still contain numbers we do not understand. That beneath the elegance of equations lies a layer of fact that has not yet been reduced to reason. The muon does not break the rules. It follows them perfectly. But by following them so faithfully, it highlights where the rules themselves may be incomplete. And so the question remains open, not as a failure, but as an invitation. Why is the muon heavy? Physics has learned to live with that question, and perhaps quietly, it is waiting for the muon itself to help answer it. If intuition ruled the universe, muons would never reach the ground. They would be born high above the earth, race downward for a fleeting moment, and vanish long before anyone noticed. And yet, detectors at sea level count them endlessly. They pass through rooftops, walls, and even deep underground laboratories, as if the planet itself were only a suggestion. This contradiction is not a detail. It is one of the clearest places where everyday intuition fails and where relativity quietly takes over. A muon at rest survives on average about 2 microseconds. That is a remarkably short time. Even traveling at the speed of light, a particle would cover only about 600 meters in that interval. The atmosphere is far thicker than that. Muons are typically created at altitudes of 10 to 15 kilometers. By classical reasoning, almost none should survive the journey. But experiments say otherwise. In the 1930s, physicists studying cosmic rays began to notice something strange. Instruments carried up mountains detected far more penetrating particles than expected. These particles behaved neither like electrons nor like protons. They passed through layers of material that should have stopped lighter radiation. Eventually, they were identified as muons. The puzzle deepened when measurements showed that muons created high in the atmosphere were still abundant at sea level. The numbers did not add up unless time itself behaved differently for fast-moving particles. This was precisely what Albert Einstein had predicted decades earlier. According to special relativity, time does not flow at the same rate for all observers. The faster an object moves through space, the more slowly its internal processes unfold when viewed from a stationary frame. This is not a mechanical slowdown. Nothing is dragging on the muon. Time itself is stretched. For a muon moving close to the speed of light, this effect becomes dramatic. Many atmospheric muons travel at more than 99.9% of the speed of light. At these speeds, time dilation is not subtle. It multiplies the muon's lifetime by 10, 20, or more. From the perspective of an observer on Earth, the muon's internal clock ticks slowly. What should be 2 microseconds becomes long enough tens of microseconds for the muon to cross the entire atmosphere and reach the ground. But relativity allows another description equally valid and equally strange. From the muon's own perspective, its lifetime is unchanged. It still survives for only 2 microseconds. What changes instead is space. The distance between its point of creation and the Earth's surface is shortened. The atmosphere is compressed along the direction of motion. The journey becomes possible not because time stretches, but because distance contracts. Which description is correct? Both. This is one of the most unsettling lessons of relativity. There is no single privileged story. Different observers describe the same event using different distortions of time and space, yet all arrive at the same physical outcome. The muon reaches the ground. The detector clicks. This is not philosophy. It is measurement. In the 1940s, physicists began designing experiments specifically to test this effect. One of the most influential involved comparing muon counts at different altitudes. By measuring how the muon flux changed between mountain elevations and sea level, researchers could infer how long muons survived in transit. The results matched relativistic predictions with striking accuracy. Without time dilation, the observed number of muons would have been smaller by orders of magnitude. With relativity included, the numbers aligned almost perfectly. Later experiments refined this further. Muons were detected at depths hundreds of meters underground, where only the most penetrating particles could reach. Their presence confirmed not only their high energies, but also the relentless accuracy of relativistic time dilation. One of the most elegant demonstrations came from simple counting experiments. Physicists measured the muon flux at the top of a mountain and again at the bottom. The reduction in numbers matched exactly what relativity predicted when decay and time dilation were combined. No adjustable parameters, no ambiguity. Muon experiments achieved something rare in physics. They made relativity tangible. Einstein's equations are often tested using clocks on aeroplanes or satellites. Those experiments are precise but abstract. Muons, by contrast, offer a visceral test. A particle that should not survive does. Not occasionally, constantly. The atmosphere becomes a natural laboratory. The Earth itself becomes part of the apparatus. There is no need for synchronized clocks or carefully engineered trajectories. Muons fall from the sky, and relativity reveals itself in their survival. Numbers anchor the story. Typical muons are created around 15 kilometers above the surface. Their speeds exceed 0.998 times the speed of light. At rest, their lifetime is about 2.2 microseconds. At these speeds, their lifetime in the Earth's frame stretches by a factor of 10 or more. That difference is the difference between disappearance and arrival. Muon densities at sea level are well measured. Roughly 1 muon passes through each square centimeter every minute. This steady flux is not a trickle. It is a continuous stream. Without relativistic time dilation, it would be nearly absent. What makes this story especially powerful is its symmetry. There is no need to choose which frame is really correct. The muon's frame and the Earth's frame tell different stories, but neither is more fundamental. Relativity insists that reality accommodates both. This lesson unsettled physicists when it was first understood. It still unsettles students today. The muon does not care which explanation you prefer. It arrives either way. Over time, muon experiments became standard demonstrations in physics education. They offered a way to test Einstein's ideas without leaving the planet or relying on astronomical distances. Cosmic rays provided the source. The atmosphere provided the stage. And the muon, indifferent and fleeting, played its role perfectly. What is remarkable is how quietly this happens. Every moment, muons are confirming relativity above our heads. There is no announcement, no signal, only particles arriving where they should not be unless time itself is flexible. This quiet confirmation is perhaps the most fitting tribute to Einstein's work. His theory did not predict exotic, unreachable effects. It predicted that the ordinary world, examined carefully enough, would reveal something extraordinary. The muon is one of those revelations. It does not bend space-time dramatically like a black hole. It does not announce itself with radiation or light. It simply lives a little longer than it should, from our point of view. And that small extension is enough to rewrite intuition. By the time a muon reaches the ground, its existence has already encoded a relativistic journey. It has carried the geometry of space-time from the upper atmosphere to the surface. It has turned equations into evidence. And when it finally decays, quietly transforming into other particles, it leaves behind more than a trace in a detector. It leaves behind confirmation that space and time are not fixed backgrounds but active participants in every high-speed process. The muon does not explain relativity. It demonstrates it again and again and again. At this very moment, as you sit still, something is passing through you. Not once, not rarely, but continuously. A muon enters from above, slips between atoms, crosses bone and tissue, and exits below, leaving behind almost nothing that you could ever feel. No warmth, no pain, no signal to the senses. And yet, at the level of physics, the passage is precise, structured, and measurable. To understand how a muon interacts with matter, it helps to begin with what it does not do. A muon does not smash atoms apart the way strongly interacting particles do. It does not trigger nuclear reactions. It does not scatter violently like low-energy electrons that bounce erratically from atom to atom. Instead, the muon moves forward steadily, losing energy in small, controlled increments. The dominant mechanism is ionization. As a muon travels through matter, its electric charge disturbs the electrons bound to atoms along its path. It transfers a small amount of energy to them, sometimes enough to knock an electron free, sometimes only enough to raise it to a slightly higher energy state. Each interaction is minor, but thousands of them occur along the muon's trajectory. This process was described with remarkable clarity in the mid-20th century, when Hans Bede and Felix Bloch developed a quantitative framework for how charged particles lose energy in matter. Their work showed that heavy, fast particles like muons lose energy at a nearly constant rate over a wide range of energies. This is one reason muons are so penetrating. Electrons, by contrast, are light. When they collide with atomic electrons, they scatter strongly. Their paths bend. They lose direction. They radiate energy as Bremsstrahlung braking radiation when deflected by nuclei. As a result, electrons slow down quickly and are easily absorbed. Gamma rays behave differently still. They carry no charge. They do not ionize continuously. Instead, they interact through discrete events, photoelectric absorption, Compton scattering, or pair production. When they interact, they often deposit large amounts of energy at once and then vanish. Muons sit between these extremes. They are heavy enough that they do not scatter easily, charged enough that they interact steadily. Their mass suppresses radiative losses that dominate for electrons. As a result, muons can traverse meters of solid material before stopping. Some traverse kilometers of rock. This penetrating power made muons fascinating long before they were fully understood. In the 1930s and 40s, physicists studying cosmic rays noticed particles that passed through shielding that stopped almost everything else. These observations played a role in identifying the muon as a distinct particle separate from the electron. As a muon passes through your body, it deposits energy along a narrow track. The energy per unit length is modest, comparable to natural background radiation. For most muons, the interaction is too weak to cause biological damage. Cells repair the occasional ionization event easily. This is why muons are not considered a significant health risk. Despite their high energies, their interaction density is low. They do not concentrate energy in a way that disrupts molecular structures on a large scale. For the vast majority of muons, the phrase "it just goes through" is accurate. The same properties that make muons biologically harmless also make them scientifically useful. Because muons leave consistent ionization trails, detectors can recognize them with high reliability. The earliest muon detectors were simple. Cloud chambers revealed thin, straight tracks cutting through vapor. Later, bubble chambers showed similar paths in superheated liquids. Modern detectors use more refined techniques. Scintillators are materials that emit small flashes of light when charged particles pass through. A muon crossing a scintillator produces a brief pulse that can be timed with nanosecond precision. This allows physicists to measure muon arrival rates, directions, and correlations with other particles. Drift chambers and wire chambers take a different approach. They are filled with gas. As a muon ionizes the gas along its path, freed electrons drift toward thin wires under the influence of electric fields. The timing of their arrival reveals the muon's trajectory with remarkable spatial accuracy. Cherenkov detectors rely on yet another effect. When a muon moves through a transparent medium, faster than light can travel through that medium, it emits a faint cone of blue light. This light, first described by Pavel Cherenkov and later explained theoretically by Ilya Frank and Igor Tamm, provides both directional and energy information. These detection methods exploit the same basic interaction ionization, but they translate it into light timing and geometry signals that electronics can record. Magnetic fields add another layer of information. Because muons are charged, their paths curve in magnetic fields. The curvature reveals momentum. The direction of curvature reveals charge. By combining tracking detectors with magnetic fields, Experiments reconstruct muon properties even after the muon itself has vanished. Electric fields play a subtler role. They guide electrons produced by ionization towards sensors. They shape detector response, but they do not significantly alter the muon's own path at high energies. The muon is too massive to be easily deflected. This resistance to deflection is another reason muons penetrate so deeply. They maintain their direction. They do not zigzag. They follow nearly straight lines over long distances, making them ideal probes of dense structures. In recent decades, this property has been exploited beyond particle physics. Muon tomography uses naturally occurring cosmic muons to image the interior of large objects. By measuring how muon flux is attenuated as it passes through material, scientists infer density variations. This technique has been used to study volcanoes, inspect nuclear reactors, and even examine the interior of ancient pyramids. In these applications, the muon becomes a messenger from the sky. It carries information about what it has passed through, encoded in whether it arrives at a detector or not. What makes all of this remarkable is how gentle the interaction remains. The muon does not announce itself. It does not disrupt the structure it probes. It samples matter quietly, one ionization at a time. From the perspective of the atom, the muon is a brief disturbance. From the perspective of the detector, it is a clean signal. From the perspective of the human body, it is essentially invisible. This combination, penetrating yet subtle, energetic yet controlled, is rare in nature. It is why muons have remained central to experimental physics for nearly a century. Physicists, like Bruno Rossi and Cecil Powell, recognized early that muons offered a bridge between cosmic phenomena and laboratory measurement. Their work helped establish the experimental foundations that modern detectors still rely on. Today, massive experiments buried deep underground still see muons. Even kilometers of rock cannot block them entirely. Each arriving muon is both a background signal and a calibration tool, reminding researchers that the universe outside the laboratory is always participating. And so, when a muon passes through you, nothing changes that you can feel. But at the level of physics, a well-defined interaction has occurred. Energy was transferred. Electrons were nudged. A track could, in principle, be drawn through space and time. The muon continues downward, indifferent to the complexity of what it traverses. It does not distinguish between air, skin, stone, or steel. It interacts according to the same rules everywhere. That indifference is what makes it such a precise witness. The muon does not adapt to matter. Matter adapts to the muon by recording its passage if we choose to listen. There is a moment in atomic physics when scale quietly shifts and familiar pictures stop working. It happens when an electron is removed and something heavier takes its place. Not a nucleus, not a proton, but a muon. At first, the idea sounds simple. A muon carries the same electric charge as an electron. It responds to the same electromagnetic force. So, in principle, if an electron is removed from an atom and a muon is introduced, instead the muon should fall into orbit around the nucleus, just as the electron once did. And that is exactly what happens. But what follows is not a small adjustment. It is a transformation of scale, so dramatic that the atom becomes a different kind of instrument altogether. Muon-electron substitution was explored seriously in the middle of the 20th century, as physicists began producing muons in sufficient numbers to study their behavior in matter. When a negative muon slows down inside a material, it can be captured by an atom, replacing one of the electrons. The result is called a muonic atom. From the outside, the atom appears unchanged. The nucleus remains the same. The chemical identity is largely unaffected because chemistry depends on outer electrons. But deep inside the structure is radically altered. The reason lies in mass. A muon is about 200 times heavier than an electron. In quantum mechanics, orbital size is inversely proportional to particle mass. Increase the mass, and the orbit shrinks. Replace an electron with a muon, and the characteristic radius of the orbit collapses inward by roughly the same factor. What was once an atomic-scale orbit now becomes a nuclear-scale orbit. The muon no longer spends its time far from the nucleus. It circulates close enough to feel the finite size, shape, and internal structure of the proton itself. In effect, the muon becomes a probe pressed tightly against the nuclear surface. This realization changed how physicists thought about atoms. Traditionally, atomic spectroscopy reveals information about electrons and electromagnetic interactions. Nuclear physics probes nuclei using scattering experiments. Muonic atoms blur this boundary. They turn atomic transitions into nuclear measurements. When the muon cascades down through its allowed energy levels, it emits X-rays. These X-rays carry information about the electric field generated by the nucleus. Because the muon orbits so close, even small deviations in the nuclear charge distribution shift the energy levels measurably. This technique became a powerful tool for measuring nuclear charge radii. Physicists in the United States were among those who refined these methods. Experiments at national laboratories and university facilities throughout the 1960s and 70s demonstrated that muonic atoms could measure nuclear sizes with unprecedented precision. The approach complemented electron scattering experiments pioneered by researchers such as Robert Hofstadter, whose work laid the foundation for understanding proton structure. But the story did not end there. Decades later, a simple system brought an unexpected surprise. Hydrogen, the simplest atom, seemed like the perfect candidate for muonic study. Replace its lone electron with a muon, and you obtain muonic hydrogen. In this system, the muon orbits a single proton. The theoretical description should be straightforward. The electromagnetic interaction is well understood. Quantum electrodynamics has been tested to extraordinary accuracy. And yet, when physicists measured the energy levels of muonic hydrogen with high precision, the result did not match expectations. The inferred radius of the proton was smaller than the value obtained from decades of electron-based measurements. Not slightly smaller, significantly smaller, enough to exceed experimental uncertainties by a wide margin. This discrepancy became known as the proton radius puzzle. The shock was not merely numerical, it struck at confidence. Quantum electrodynamics had passed every test thrown at it. Electron scattering experiments had converged on a consistent proton size. And now, by simply swapping an electron for a muon, the numbers changed. Why? The puzzle triggered intense scrutiny. American researchers at institutions such as MIT, Jefferson Lab, and national laboratories revisited electron scattering data. Others refined theoretical calculations, re-examining subtle corrections involving vacuum polarization, two-photon exchange, and relativistic effects. Muon experiments were repeated. Measurement techniques were cross-checked. No obvious error emerged. What made the situation unsettling was how sensitive the muonic atom was. Because the muon orbits so close to the proton, small effects that barely influence electrons become amplified. Tiny distortions of the electromagnetic field, slight rearrangements of charge, and quantum fluctuations in the vacuum all leave detectable signatures. In other words, the muon was not contradicting physics casually. It was interrogating it at a scale electrons could never reach. This sensitivity is the key to why muonic atoms act like a special kind of microscope. They do not magnify visually, they magnify response. They turn small structural features into measurable shifts. From a theoretical perspective, the equations describing electrons and muons are nearly identical. But the muon's mass moves the experiment into a different regime. Effects that scale with mass become dominant. The nucleus is no longer a distant point. It becomes an extended object with structure. American physicists have long appreciated the power of such precision tools. From atomic clocks to laser spectroscopy, US laboratories have emphasized measurement as a way of revealing new physics. Muonic atoms fit naturally into this tradition. They offer a way to stress-test theory without inventing new forces or particles. The proton radius puzzle has not yet fully resolved. Improved measurements have narrowed discrepancies, but debates continue. Some interpretations suggest subtle systematic issues in earlier electron experiments. Others explore whether new physics might distinguish electrons from muons, slightly violating a principle known as lepton universality. What remains uncontested is the lesson itself. By replacing an electron with a muon, the atom becomes an entirely different instrument, one that listens more closely, one that responds more sharply, one that notices details that were previously averaged away. This is not because the muon is exotic, it is because it is familiar in a heavier form. The same rules apply, the same equations govern motion, only the scale changes, and with scale, sensitivity emerges. Muon-based measurements have now been extended beyond hydrogen. Muonic helium and heavier muonic atoms have been studied to refine nuclear models. These experiments feed back into astrophysics, particle physics, and fundamental constants. They remind us that progress in physics often comes not from new ideas alone, but from new ways of looking. Sometimes that means building larger machines. Sometimes it means slowing particles down. And sometimes it means choosing a heavier messenger. The muon does not reveal new forces directly. It reveals the limits of our assumptions. It asks whether electrons tell the whole story or only part of it. In muonic atoms, the nucleus is no longer an abstract center. It becomes a measurable landscape. The proton acquires edges. Charge distributions acquire meaning. The atom stops being spacious and becomes intimate. And all of this happens quietly, inside matter that looks unchanged from the outside. The muon enters, the electron leaves, the orbit contracts, and the atom becomes briefly a microscope pointed inward toward the very heart of matter. There are moments in physics when the spotlight turns inward, not toward distant galaxies or extreme energies, but toward a single number, measured so carefully that even its last decimal place is watched with suspicion. For the muon, that number is called G-2. At first, it sounds abstract, a correction, a technical detail. But for decades, it has been one of the most sensitive places where the standard model is asked a simple question: are you complete? Every charged particle with spin behaves like a tiny magnet. This is not a metaphor. It is a measurable property. When a particle with charge and spin is placed in a magnetic field, its spin precesses, slowly rotating, much like a compass needle under torque. The strength of this magnetic behavior is captured by a number called the gyromagnetic ratio, or simply G. For a perfectly simple particle described by the most basic equations, G would be exactly 2. But the universe is not that simple. Quantum mechanics insists that empty space is never empty. Even in a vacuum, fleeting particles appear and disappear. These virtual particles cannot be observed directly, but they influence real particles subtly and continuously. As a muon moves through this quantum vacuum, it is constantly interacting with these fluctuations. Photons flicker into existence. Particle-antiparticle pairs form and vanish. Heavier particles, even ones that cannot be produced directly at the muon's energy, briefly leave their imprint. Each of these interactions shifts the muon's magnetic moment slightly. The result is that G is not exactly 2, but a bit larger. The difference G-2 is small, but it is calculable, and it is measurable. This is where the muon becomes extraordinary. The same effect exists for the electron. Its magnetic moment has been measured and calculated to astonishing precision. The agreement between theory and experiment for the electron is one of the greatest triumphs of quantum electrodynamics. So why look at the muon? Because mass changes sensitivity. The muon is about 200 times heavier than the electron. That mass amplifies the influence of heavy virtual particles. Effects that are completely negligible for electrons become detectable for muons. In a sense, the muon listens more carefully to the deep structure of the vacuum. This insight motivated generations of experiments. In the late 20th century, American physicists at Brookhaven National Laboratory constructed one of the most ambitious precision experiments ever attempted. Muons were injected into a circular storage ring, held in orbit by a uniform magnetic field. As the muons circulated, their spins precessed. By measuring that precession with extreme accuracy, researchers extracted the muon's magnetic moment. The result was unsettling. The measured value of G2 did not align perfectly with theoretical predictions. The discrepancy was small parts per billion, but persistent. Too large to dismiss casually, too small to declare a discovery. Years later, a new generation of American scientists took up the challenge at Fermilab. Using a refined version of the same storage ring transported across the country with extraordinary care, they repeated the measurement with improved precision. Again, the muon whispered disagreement. The experimental value continued to differ from the standard model prediction. The gap narrowed in some analyses, widened in others. The question sharpened rather than resolved. At this point, physics faced a familiar crossroads. Is the discrepancy a measurement problem? Precision experiments are fragile. Tiny, systematic errors can masquerade as new effects. Magnetic fields must be mapped perfectly. Muon beams must be controlled exquisitely. Timing must be synchronized at the nanosecond level. Or is the discrepancy theoretical? Calculating G2 requires accounting for contributions from all known forces. Quantum electrodynamics is well behaved, but the strong interaction governed by quantum chromodynamics is far more subtle. Hadronic effects are difficult to compute from first principles. Approximations must be used. Different methods give slightly different answers. American theorists working alongside international collaborators have spent years refining these calculations. Lattice QCD simulations, dispersion relations, and data-driven approaches have all been applied. The theoretical prediction itself has become a living object, evolving as methods improve. And then there is the third possibility, that the muon is telling the truth. If the discrepancy survives scrutiny, it may indicate physics beyond the standard model, something new influencing the muon's magnetic moment through the quantum vacuum. What could that be? Speculation must be careful here, but certain patterns are suggested by theory. New particles that couple preferentially to muons rather than electrons. New forces that operate subtly at short ranges. Slight violations of a principle long assumed to hold lepton universality. Lepton universality states that electrons, muons, and tau interact identically with forces differing only in mass. If this principle is violated, even slightly, muons could behave differently in ways that electrons never reveal. Such violations would not overturn physics overnight. They would whisper, not shout. But G2 is precisely the kind of experiment sensitive to whispers. This is what makes the muon magnetic moment so powerful. It does not look for spectacular events. It looks for imbalance, for asymmetry, for numbers that refuse to align perfectly. American physicist Richard Feynman once emphasized that nature's laws are revealed not by their elegance alone, but by their agreement with experiment. The muon G2 story is an embodiment of that philosophy. The equations are beautiful, the measurements are relentless, and where they disagree, curiosity intensifies. What is especially striking is how indirect this probe is. The muon does not collide with new particles. It does not decay into exotic states. It simply spins, and in that spinning it samples the entire quantum vacuum. The experiment becomes a census of everything that can influence a muon, including things we cannot yet name. This is why G2 occupies such a unique place in modern physics. It is not a discovery machine in the traditional sense. It is a consistency test, a stress test, a place where the standard model must hold together without cracks. If the crack widens, it will not be dramatic. It will be incremental, one decimal place at a time. And yet history suggests that revolutions often begin this way, with small numbers that refuse to disappear. For now, the story remains open. Experimental uncertainties continue to shrink. Theoretical predictions continue to sharpen. Conferences revisit the same plots, updated year after year. The muon remains patient. It does not argue. It does not insist. It simply behaves as it always has, allowing physicists to watch its motion and ask whether the universe has told us everything it knows. If new physics exists at accessible scales, the muon may be among the first to sense it, not because it is exotic, but because it is heavier, more sensitive, and quietly attentive to the restless structure of the vacuum. And if the standard model survives intact, that too will be a revelation, because it will mean that even under extraordinary scrutiny, the universe remains internally consistent. Either way, the muon G2 story is not about anomaly for its own sake. It is about listening carefully enough to notice when nature hesitates. The muon spins, the numbers accumulate, and physics waits. There is a quiet companion that never leaves the muon. Wherever a muon is born, something else slips away at the same moment, almost unnoticed, almost unreachable. That companion is the muon neutrino. The connection between the two is not incidental. It is written directly into the rules of the weak interaction. Whenever a charged pion or kaon decays and produces a muon, a neutrino appears alongside it. Not just any neutrino, but one with a specific identity, the muon neutrino. This pairing is one of the earliest clues physicists had that neutrinos come in different types or flavors. The muon is not simply accompanied by a neutrino as an afterthought. The neutrino carries information that balances the transformation. It ensures that fundamental accounting rules, conservation of lepton family number, are satisfied. The story begins once again high above the Earth. Cosmic rays strike the atmosphere and generate showers of secondary particles. Among them are pions and kaons, unstable hadrons that decay quickly. A charged pion decays almost exclusively into a muon and a muon neutrino. The muon continues downward, often reaching the surface. The neutrino barely interacts at all and passes straight through the planet. This simple decay chain links two very different messengers. One is heavy charged and detectable. The other is nearly massless, neutral and elusive. Yet they are born together, sharing momentum and energy according to the same physical laws. In this process, the neutrino carries away information about the decay. Its energy distribution reflects the kinematics of the pion. Its direction encodes the geometry of the interaction. Even though it rarely interacts afterward, its properties are fixed at birth. For decades, physicists assumed neutrinos were almost irrelevant. They were thought to be massless, passive participants that simply balanced equations. But this assumption did not survive careful observation. In the 1990s, a remarkable discovery emerged from underground detectors studying atmospheric neutrinos. These experiments, including work by American physicists at facilities such as the Super Kamiokande collaboration, observed something unexpected. Muon neutrinos produced in the atmosphere were arriving at detectors in smaller numbers than predicted, and the deficit depended on direction. Neutrinos coming from directly above behaved differently from those that had traveled through the Earth before detection. The explanation was revolutionary. Neutrinos oscillate. A neutrino, born as a muon neutrino, does not remain a muon neutrino forever. As it propagates, it can transform into other flavors, such as electron neutrinos or tau neutrinos. This behavior requires neutrinos to have mass small but not zero, and it requires that the flavor states be mixtures of mass states. Muon neutrinos were central to this discovery. Atmospheric neutrinos originate largely from the same decay chains that produce muons. By studying the disappearance of muon neutrinos over long distances, physicists uncovered one of the first clear signs of physics beyond the original Standard Model. This connection between muons and neutrinos is not limited to natural sources. It is deliberately engineered in laboratories. In accelerator-based neutrino experiments, muons are part of the design. The process begins with a high-energy proton beam striking a target, producing pions and kaons, much like cosmic rays striking the atmosphere. These mesons are then focused using magnetic horns, which select particles of a chosen charge and direction. As the pions decay, they produce muons and muon neutrinos. The muons can be absorbed or deflected, while the neutrinos continue forward, forming a neutrino beam. The flavor of the beam is determined by the decay. A muon neutrino beam is born alongside muons. This method was refined through decades of work, including major contributions from American laboratories such as Fermilab. Experiments like MINOS, NOVA, and later DUNE rely on this technique. Muons act as signposts. By monitoring the accompanying muons, physicists infer the properties of the neutrino beam itself. In this sense, muons are not merely byproducts. They are diagnostics. Their energy and direction reflect the neutrino beam's profile. Detectors near the source measure muons to calibrate neutrino production. Far detectors observe neutrinos after they have traveled hundreds or thousands of kilometers, testing how their identities change along the way. This approach has transformed neutrino physics from a passive observational field into a controlled experimental science. Muon neutrinos, generated in accelerators, have confirmed oscillation parameters first hinted at by atmospheric neutrinos. They have measured mass differences between neutrino states. They have explored how neutrinos interact with matter. The muon once again serves as a bridge. It links what can be measured directly to what must be inferred indirectly. American physicist Leon Lederman played a pivotal role in establishing neutrino beams and identifying distinct neutrino flavors. His work helped confirm that the neutrino associated with the muon was not the same as the one associated with the electron. This insight laid the groundwork for everything that followed. What makes this partnership between muons and neutrinos so compelling is the contrast. The muon is short-lived but visible. The neutrino is long-lived but nearly invisible. Together, they map a process that spans vast distances and tiny timescales. Muon decay itself also produces neutrinos. When a muon decays, it produces an electron, an electron neutrino, and a muon neutrino. This makes muons useful sources of well-characterized neutrino spectra. Some proposed experiments even explore the idea of muon storage rings as future neutrino factories. In such designs, muons circulate until they decay, producing intense, precisely known neutrino beams. These concepts push the boundary of what controlled neutrino experiments could achieve. Through all of this, one theme remains consistent. Neutrinos are never observed alone. They are inferred through absence, imbalance, and transformation. Muons make those inferences possible. They mark the birth of neutrinos. They signal the structure of beams. They confirm the chains of decay that neutrinos emerge from. In atmospheric physics, muons reach the ground while neutrinos pass through it. In accelerator physics, muons are filtered out while neutrinos continue onward. In both cases, the relationship is intimate and unavoidable. Muon neutrinos taught physicists that particles once thought immutable can change identity. They revealed that mass hides where it was not expected. They forced revisions to the Standard Model's most basic assumptions. And all of this traces back to a simple decay, a pion becoming a muon and a neutrino. From that moment, two paths diverge. One particle interacts, ionizes, and eventually decays. The other slips through matter, almost untouched, carrying its identity across continents and through planets. Yet, they remain linked by origin. The muon tells us where the neutrino came from. The neutrino tells us what the muon made possible. Together they form one of the quietest but most powerful partnerships in modern physics, one that continues to reshape how we understand mass identity and change in the universe. There are ways of seeing that do not use light. Long before X-rays were discovered, long before scanners learned to rotate around the human body, the universe had already prepared another probe, one that arrives continuously from above and passes through stone as if it were thin air. That probe is the muon. Muon tomography begins with a simple observation. Muons penetrate matter far more effectively than most other particles. They pass through concrete, steel, and kilometers of rock, losing energy slowly and predictably. Where denser material exists, fewer muons survive. Where empty spaces exist, more pass through. This contrast is the foundation of muon imaging. Unlike medical CT scans, which require an artificial source of radiation rotated around an object, muon tomography uses a source that cannot be turned off the sky itself. Cosmic rays continually generate muons in the atmosphere, sending them downward in nearly straight lines. Each muon arrives with a direction, an energy, and a history written into how much material it has crossed. The idea is not to illuminate an object, but to listen to what the muons tell us after they pass through. If a detector is placed beneath or beside a large structure, it records how many muons arrive from different directions. Where the structure is dense, fewer muons appear. Where it contains voids, tunnels, or less dense material, the muon count rises. Over time, a three-dimensional picture emerges. This method resembles a CT scan in concept. Both rely on attenuation, how much a penetrating signal is reduced by material. Both reconstruct internal structure from many lines of sight. But the differences are just as important. In CT scans, X-rays are actively generated, precisely timed, and tightly controlled. The scan completes in seconds or minutes. Muon tomography is passive. It waits. The muons arrive when they arrive. Data accumulates slowly, often over weeks or months. There is also no rotation. The sky provides all angles naturally, but not uniformly. Most muons arrive from above. Few come from shallow angles. This shapes detector placement and limits resolution in certain directions. Despite these constraints, muon tomography has proven remarkably effective. One of the earliest and most famous demonstrations involved archaeology. In the 1960s, physicist Luis Alvarez, an American Nobel laureate, led an experiment to search for hidden chambers inside the Pyramid of Khafre in Egypt. Detectors were placed inside the pyramid to count muons arriving from different directions. The logic was straightforward. If a hidden void existed above the detector, more muons would arrive from that direction. If solid stone filled the space, fewer would pass through. The experiment did not find new chambers, but it proved that muon imaging could work at monumental scales. Decades later, the technique returned with modern detectors and computing power. In 21st century experiments, including international collaborations with American researchers, muon tomography revealed previously unknown voids inside the Great Pyramid of Giza. These discoveries captured public attention and confirmed the method's sensitivity. Beyond archaeology, muon tomography found a natural home in geology. Volcanoes are massive, dense, and dangerous to probe directly. Traditional methods rely on seismic waves, gravity measurements, or surface observations. Muons offer another approach. By placing detectors around a volcano, scientists measure how muon flux varies with direction. Regions of lower density, such as magma chambers or conduits, allow more muons to pass. American geophysicists and international teams have used this technique to map internal volcanic structures, providing insights into eruption dynamics and magma movement. The method is slow, but it is non-invasive and continuous. It listens rather than disturbs. Muon tomography has also played a role in security and infrastructure. After nuclear accidents, such as the Fukushima disaster, muon imaging was proposed as a way to assess the internal condition of damaged reactor cores without direct access. Muons can penetrate containment structures and reveal where dense fuel material has accumulated. In the United States, researchers have explored muon tomography for monitoring nuclear waste storage, detecting smuggled nuclear material, and inspecting critical infrastructure. The technique's strength lies in its passivity. It does not introduce radiation. It does not interfere with operations. It simply observes what is already happening. Technically, what must be measured is precise but conceptually simple. Detectors track the direction of incoming muons. They count how many arrive from each angle. In some designs, they also estimate energy by observing how muons scatter as they pass through material. Dense materials cause greater deflection. Over time, these measurements are assembled into a map, not a photograph, but a density distribution, a statistical image built from millions of individual particle paths. This statistical nature is both a strength and a limitation. Muon tomography does not produce sharp images quickly. Resolution improves only as data accumulates. Noise must be averaged away. Background muons, detector inefficiencies, and environmental variations all contribute uncertainty. American physicists working in particle detection have contributed significantly to improving these methods. Advances in scintillator materials, tracking chambers, and data analysis algorithms have increased sensitivity and reduced required exposure times. Still, patience remains essential. Another limitation is geometry. Muons arrive primarily from above, limiting the angles available. This makes horizontal features easier to detect than vertical ones. Detector placement must be carefully planned, and some structures remain difficult to image fully. Yet within these constraints, muon tomography offers something unique. It operates at scales no laboratory scanner can match. It sees through kilometers of rock. It images objects too large, too dense, or too dangerous to open. It does so using particles created far above the Earth, accelerated by astrophysical processes beyond human control. In a sense, muon tomography turns the entire planet into part of the instrument. The sky supplies the source. The object shapes the signal. The detector listens. This approach reflects a tradition in American experimental physics, using nature itself as part of the apparatus. From cosmic ray studies to neutrino observatories buried deep underground, researchers have long recognized that some experiments require cooperation with the environment rather than isolation from it. Muon tomography belongs to this lineage. It is not fast. It is not dramatic. But it is steady, reliable, and revealing. A muon passes through stone. Another does not. A pattern emerges. Slowly, the invisible becomes measurable. There is also something fitting about the muon's role here. The muon does not interact strongly. It does not disrupt what it probes. Its samples matter gently, one ionization at a time. This restraint makes it an ideal messenger. In archaeology, it respects ancient structures. In geology, it observes without drilling. In security, it inspects without exposure. The muon does not announce itself. It does not illuminate. It does not invade. It simply passes through, carrying information encoded in survival and absence. As detectors grow more sensitive and analysis methods more refined, muon tomography continues to expand. New applications emerge quietly, often where other techniques struggle. Each success reinforces the same idea that seeing does not always require light. Sometimes it requires patience, and particles from the sky. Muon tomography does not replace other imaging methods. It complements them. It fills gaps where nothing else works. It listens to the universe's background radiation and asks it to reveal what lies hidden beneath. And in doing so, it turns one of the most fleeting particles in nature into a tool for uncovering the most enduring structures humanity has ever built or feared to open. The muon arrives, the stone responds, and slowly the interior speaks. As the story of the muon draws to a close, the questions it leaves behind do not disappear. They do not resolve neatly into a single conclusion. Instead, they widen the view, reminding us what this small, fleeting particle has quietly been asking us all along. Is the muon truly fundamental? Every experiment performed so far says yes. When muons are smashed together, deflected by fields, or slowed inside matter, no internal structure reveals itself. They behave as points. Not because we insist they are simple, but because nature has not yet shown us otherwise. And yet, history teaches caution. Protons were once thought indivisible. Atoms were once thought final. Each time deeper layers emerged, only when measurements grew more precise. The muon sits in that same uncertain position. It obeys the rules perfectly, but it does not explain itself. It looks elementary, yet it belongs to a repeating pattern that feels unfinished. If future experiments ever reveal substructure, it will not be because the muon failed, but because it patiently waited for us to look closer. Another question lingers just as persistently. Why does the universe produce so many muons if they live for such a short time? Cosmic rays arrive from distant astrophysical events, supernova remnants, active galactic nuclei environments shaped by enormous magnetic fields. When they strike Earth's atmosphere, the result is not silence but abundance. Cascades of particles form, and among them muons appear again and again. Nature seems comfortable creating something transient, only to replace it endlessly. This abundance tells us something subtle. The universe is not optimized for permanence at the smallest scales. It is optimized for process. Muons are not meant to last. They are meant to connect stages, linking high-energy events in space to measurable effects on Earth. Their short lives are not a weakness. They are a feature of a universe that values transformation over storage. Now imagine for a moment that muons vanished tomorrow. Particle physics would lose one of its most sensitive probes. Precision tests like the Muon G2 experiment would disappear, taking with them one of the few windows we have into the quantum vacuum's deeper structure. Neutrino physics would lose its most reliable companion particle. Accelerator-based neutrino beams would need to be reimagined entirely. Muon tomography would fade. Imaging volcanoes, pyramids, and reactor cores without invasive techniques would become far more difficult. Even basic detector calibration would suffer, as muons provide a constant, predictable background signal used across experiments worldwide. The loss would not be dramatic. No technology would fail overnight, but a quiet layer of measurement would be gone. A tool that asked precise questions without forcing violent interactions would no longer be available. This leads naturally to a deeper reflection. What is the muon telling us about the limits of the standard model? On the surface, the standard model works remarkably well. It predicts muon decay, rates, interaction strengths, and most observable properties with extraordinary accuracy. And yet the muon repeatedly presses on its edges. Its unexplained mass, its role in flavor structure, the persistent tension in G2 measurements. Each is small, none is catastrophic. Together they form pressure. American physicists such as Sheldon Glashow and Steven Weinberg helped build the theoretical framework that still guides us today. Their work emphasized symmetry, consistency, and predictive power. The muon respects all of these, but it also exposes where explanation gives way to description. Is that a door opening, or simply a demand for greater precision? At present, we do not know. It may be that improved calculations and measurements will eventually align perfectly, reinforcing confidence in the existing theory. Or it may be that the muon is pointing quietly towards something missing. Not a dramatic breakdown, but a gentle extension, a refinement. In either case, the muon's role remains the same. It does not shout, it tests. Placed in the broader landscape of physics, the muon occupies a unique position. It connects spin through its magnetic behavior to quantum fluctuations. It connects atoms by forming muonic atoms that reveal nuclear structure. It connects space by arriving from cosmic processes far beyond Earth. It connects the universe by translating distant astrophysical energy into local measurements. It connects the Higgs field through its unexplained mass. And it may even connect indirectly to quantum gravity by reminding us that mass, scale, and structure remain incomplete stories. Few particles touch so many domains without dominating any of them. That is why the muon deserves its own story. Not because it is the most important particle, but because it is the most revealing. It is ordinary enough to study, unusual enough to question, and sensitive enough to expose subtle truths. The muon does not build the world we see, but it helps us understand how that world holds together. As this journey comes to rest, it is worth noticing how quiet the muon's contribution has been. It does not glow, it does not accumulate, it does not leave monuments. It passes through, does its work, and disappears. And yet physics would be poorer without it. If this long exploration has brought you even a small sense of clarity or a gentle feeling of connection to how deeply ordered the universe truly is, I'm grateful you spent this time here. A soft moment of attention, like a muon passing through matter, can still leave a meaningful trace. Wherever you are listening from, and whatever time of day or night this finds you, I hope these ideas settle comfortably with you as the world grows quiet. Thank you for being here, for your patience, and for your curiosity. The universe continues its work steadily and precisely, and somewhere above us, muons are still falling through the sky.